Today, we are going to look at context-free grammars. In the previous video, we look at PDAs, and we know that PDAs accept context-free languages. Okay, so the reason we didn't call the languages accepted by PDA as a PDA languages is that the languages accepted by PDAs can actually be generated by a grammar called context-free grammar. We're going to explain why we call it context-free grammar later, because it will be clearer when we talk about context-sensitive grammars. In that context, then we can understand why such grammars are called context-free. Okay, so first of all, let's look at the form of grammar rules. In the PDA, in the DFA, in the deterministic finite automaton, we can write a transition delta PA equals Q as P arrow AQ. Okay, so that means that AQ can be generated from P. So this form is called a grammar rule. Likewise, in an NFA, we can write a transition delta PA equals a set of states Q1 up to QK as the following grammar rules. P arrow AQ1 bar means or, AQ2 blah 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 or AQK. Similarly, in a PDA, we may also write a transition delta PA gamma, small gamma, which is a stack symbol, equals a set of pairs, state and the strings. So this is state, this is string in the stack. So Q1, S1 up to QKSK as the following grammar rules. P arrow A gamma Q1 S1 or blah 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 or A gamma QKSK. So we'll provide more details later. So rules in this form. So this A, think of A as a variable. Arrow 0A1, 0 here is a symbol, or we call it terminal symbol, which is not a variable. So A here is a variable, or A arrow B1, again, B is a variable, 1 is a non-variable symbol. We call it terminal symbol. A arrow 1B and A arrow 0 or A arrow epsilon, all of these rules are called context-free grammar rules. So now let's see why it is called context-free, because when we, so all of the rules here at the left-hand side, you only have one variables, right? So which means that, for instance, from this variable A, I can derive a new things. So we can derive new things. So that means that when I determine this derivation, we don't care what's on the left of A and what's on the right of A. We just look at A itself, then we can apply these rules. Hence, this rule is context-free. Now, these are the context. These are the context. On the left of A and on the right of A, I don't care what they are, as long as I see A here, then I can generate new string. So this is why such form of grammar rules is called context-free. And of course, if you have a context-sensitive rule would be, so on the left-hand side would be a string. So this would be a, let's say, maybe you can have A or B, and then you can only, in this situation, you can generate a new rules, let's say B, C, right? So that means now you cannot just look at one symbol, you have to look at a piece of text in order to go to the, in order to generate a new string. So this is called context sensitive. Okay. All right, so now let's look at a formal definition of a context-free grammar. A context-free grammar is a four-tuple G. So you have V, sigma, R, and S. The meaning of these components, are as follows. So V here is a finite set called variables. So it's a finite set of variables, just like capital A and B in the previous examples. And capital sigma is a finite set of terminal symbols, such like a small a, small b, so they are not variables. And of course, they don't, this V and sigma, they don't intersect. Okay, so, and they are both finite. And R here is a set of rules, which each rule being a variable on the left, that means it's context-free, and a string of variables and terminals on the right. So the right-hand side could contain variable, or could contain one variable or more than one variable, and it could contain symbols, terminal symbols or terminals, okay? And this S here indicates that it is the start of variable. It begins from S. So now let's look at the concept of derivation or generation. So let A arrow W be a rule, and let UV be strings of variables and terminals. Then we say that UAV yields or derives UWV, denoted by UAV double arrow UWV. Okay, because what we are going to look at here, we just look at A, and these rules apply, so we can replace A with W, hence we get this. And the way we are going to denote it is UAV double arrow UWV. So in other words, we can say that UWV is derived from UAV, or UWV is generated from UAV. So now we can say that a string U derives a string V, and we denote this by double arrow start. So this start just indicates I don't care how many steps, right? So we don't count the steps. As long as this V is the end result by applying rules several times, and we can get V from U. So this means that if either U is equal to V, so which means that you don't apply any rules, or you don't apply any rules, or if a sequence U1, U2, UK exists, such that U derives U1, U1 derives U2, blah, 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 and you get to UK, and UK is V, okay? UK derives V. All right, so So this asterisk just means that this k is for some k greater than or equal to 0. So now we put, okay, so this should be sigma star. So star should be up here. Okay. And for any terminal for W, which is a string of terminal symbols or terminals, and if this W can be derived from the star variable S, and we put all W here in this language, and this language is called a language generated by this context-free grammar G. We write it as L of G. So this is the language, and then of course we're going to show that it is equivalent to context-free languages, meaning it is equivalent to the language accepted by PDAs. So now let's look at an example. Remember, when we look at the pumping lemma for regular languages, we know that this language is not regular, and also we know that this language is accepted by a PDA from the previous video. So now we're going to see that we can also use a context-free grammar to generate this language. So the construction is straightforward. So here V only contains one symbol, S, which is the star's variable. Okay, so one variable. And sigma is binary, so that's a 0 and 1. So the grammar rule is straightforward. So S arrow 0 S1 and S epsilon, so which means that it can generate an empty string. For instance, 000111 is derived as follows. So you start from S, and then you apply the first rule, 0S1, and you apply it again, you get 0. So you apply it again, you get that, right? You apply again, you get that. Of course, these are parentheses, it's not there. Okay, and then finally you apply this S to epsilon rule, then you generate this string. So you can generate any string in this form. Okay, so this is the straightforward rules, grammar rules. So now let's look at a fragment of context-free grammars for the English language. So here, anything that's in is angles is a variable, and these are terminals. Okay, so small letter terminals. So this variable sentence, arrow, noun phrase, and followed by verb phrase. So this sentence is you have a subject, you have a predicate, but you don't have an object, right? But of course you can also put an object there, but this is a fragment. So noun phrase could be a complex noun or complex noun followed by preparation phrase. And a verb phrase could be a complex verb or could be a complex verb followed by preparation phrase. And preparation phrase could be preparation followed by complex nouns. Complex noun, arrow, which so that means it could be article followed by noun, and complex verb could be verb or verb followed by noun phrase. And article, you have two articles in English, a or the. And noun, here, of course, it would be all the nouns in your in the English dictionary, but here we just pick the fragment. So this is boy, girl, and flower. And verb could be, the verbs would be all verbs in the English dictionary. But now we just look at touches, likes, and sees. Well, of course, this is a third person form. And preparation with. Okay, so this is a small fragment of this context-free language for the English language. So now let's look at a concrete example of a sentence, a boy sees. Okay, so let's see how we can derive this from that grammar we looked at earlier. So we begin with a sentence because it is a start symbol. So we're looking at a sentence. So sentence goes to a noun phrase and verb phrase. And a noun phrase could be, is a complex noun. And then so this is using a noun phrase is a complex noun. So we use that. And then complex noun. Here is article followed by a noun. So we have article followed by a noun. And then an article could be either a or the, but here we have a. So we put a here and noun. And noun could, now we could have boy, girl, or flower. So we put boy here and then the verb phrase. And verb phrase could be, here could be a complex verb or complex verb followed by preparation phrase. So we just use complex verb here, and complex verb could be verb or verb followed by noun phrase. So we get just verb, and verb, we know that sees is a verb. So this is how this sentence is generated by this grammar rules. All right, so now let's look at another example, which is a way to generate a nested parentheses. Okay, so in your computing one, you have learned, you probably computing two when you learn stacks, either one or two. You use stacks to generate well-balanced or well-nested parentheses. Okay, here is the grammar rules. Okay, when you use stacks, of course, you are using PDAs, right? So remember PDA uses stack as a memory. And in writing your program, you use stack also as your data structure. Data structure is your memory device, right? So in this case, we can generate well-nested or properly nested parentheses as follows. So we just use one, okay, variable s, which is also a start variable. And the terminals, we just parentheses, left parentheses, right parentheses. All right, so the rules is s generates parentheses s, or s followed by s, or epsilon. Okay, so then of course you can generate any properly nested parentheses. For instance, for this string of terminals, it can be derived as follows. So first we use this double S rule. Use it again, we generate three S's. And then this one generates a parentheses, so we get that. So, and then we use this epsilon rule, we get that. And then the second one, we generate this and do it again, we do that. And then you go to epsilon, we have this. And the last one, we generate this. And then we use the epsilon rule, then we generate this. Okay, so this is easy to understand. So that's one application of using stack, right? So in your computing one. All right, so now let's look at the following grammar for generating expressions. Okay, expression, of course, you have terminals. So your terminals will be maybe numbers, but we are going to use we are using A to represent an item, and then you have operations, plus and multiplication here. Of course, you can put subtraction, division, and some other operations. And of course, we use parentheses to indicate preference. Okay, so the rules are expression arrow. So you use plus expression, and then or a term. A term, it would be term times factor, and the factor would be either the expression or a terminal A. Okay, so in this particular case, for instance, A plus A times A, this is how you generate, okay, expression. You do the A plus the, so you use this rule first, right? So expression plus term, and then expression, you can have term. So term can be factor, that's A. And this term can be term multiplies term times factor and factors, right? So term is term times factor, and term goes to factor, that's A, factor goes to A. So right, similarly, you have this using these parentheses first. So in this particular case, you know that you are going to, because of parentheses, you know, the preference is given to A plus A first. In this, according to the rule, you are going to do this A times A first. All right. Okay. So now we have seen several examples of context-free grammars and the strings it generates, the strings of terminals it generates. So now let's consider how we can design a context-free grammar to generate a given language. Of course, the approach would be to combine simple context-free grammars to construct a more complex context-free grammar using the following operations. Now remember, these are called regular operations: union, concatenation, and star. And so we let, let's say we let GI be K context-free grammars over the same alphabet. Okay, so which means that we have, let's say we have a K simple CFGs, and then we can combine these CFGs to construct a new CFG using these techniques respectively. For instance, we can use union. Of course, the new set of variables will be the union of all the variables in these GIs, and of course the rules will be the union of them, but we need to add some new rules. Okay, so this S here is different from SI, so this is a new symbol. So for union, what we're going to write here is that instead of using R prime, we're going to add new rules, which is S arrow, S1, or S2, blah, 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 or SK. So which means that you just go to any one of these will be fine. So that's a union. And concatenation will be concatenate. Let's say the concatenation is in this order, G1, G2, up to GK. So then what we're having here is S arrow S1 followed by S2, blah, 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 followed by SK. And for star, okay, so that means that it will need to generate all sorts of combinations of S. Okay, so S then go to SS, so you can keep using these rules, you can generate all kinds of S, but each of these S could either be S1 or up to SK, and then of course it can also go to epsilon. So that's a star. All right. So so then we can also turn an FA or a PDA to grammar rules. So let's look at some examples. So let's say we want to generate a context-free grammar for this language. 0 and 1 to the n is n greater than or equal to 0. Or this is a union, of course, the 1n is 0n, right? So that means that we know, so this is a union of two context-free languages. We know how to generate this. We also know how to generate that. So for this, we're using these rules. For that, we are using these rules, and then we combine them. We add a new star variable. It goes to either S1 or S2. Then you copy S1, copy these rules, and copy these rules down. So this is straightforward. So now let's look at a concept called ambiguity. So context-free grammars could produce ambiguity. So in other words, there are more than one way, there are multiple ways, okay, to generate the same sentence. That means even you fix the order, right? We always apply rules from left to right, but you still have multiple ways. If you still have multiple ways to generate the same string, then that string has multiple meanings, and hence it is ambiguous. You don't know which meanings you are referring to. So now let's look at this example. So expression arrow, expression plus expression or expression times expression or parentheses expression or a factor A or a terminal A. So in here, of course, it is plus and multiplication. They are in the same order or preference. Okay, so then of course you can look at A plus A times A. This you have two parentheses. You have two derivations. So for this, for instance, you start from expression, you apply this first, because they either this or that, or this one you apply plus first. Okay, so in the same order of replacing a variable. So there you get two derivations. So then this expression is ambiguous. You don't know whether you should do this first or do that first. We all know that for arithmetic, the results are different. So this is ambiguous. So this is a rule. So of course, for the for the programming language, it is a context-free grammar. So you have to have a way to get rid of these ambiguity. And the previous example is one way to do that, right? So so this is one way to get rid of ambiguity by setting up preference. All right. Next, we are going to see a special form of context-free grammar. And then we also show that any context-free grammar can be converted to an equivalent context-free grammar in this form. And this form is called Chomsky normal form. So a context-free grammar is in Chomsky normal form if every rule is of the form A arrow BC or A arrow A, so this is a terminal, or S epsilon, where this S does not appear on the right-hand side. Okay, so which means that it is a So the derivation, this will make derivation controllable, because for each A, you only either go to 2. Now again, S does not appear at the right-hand side. So the star symbol only appears at the left-hand side. Or you can just go to a symbol B, right? So this is a much simpler form. And this is called Chomsky normal form. And the good thing here is that any CFG, any context-free grammar G, can be converted to Chomsky normal form using a straightforward algorithm. Okay, so that's important. Okay, so this is using a straightforward algorithm such that they generate the same languages. Okay, so it's converted means, let's say, converted to a normal form G prime by a efficient algorithm. So let's just say by an algorithm, and such that they accept the same language. L of G is the same of L of G prime. So this result tells us that if we are looking at context-free grammar, you can always assume that you are looking at context-free grammar in Chomsky normal form, in the Chomsky normal form. Okay, so now here is the proof. The proof is just constructing an algorithm. So we first add a new star variable S0, which is not in V. So we put S0 arrow S. So this ensures that this new star variable does not appear at the right-hand side. So because this S may appear at the right-hand side, but this S0s will not. And then we're going to remove A arrow epsilon. So we are going to, because in this form, when the right-hand side is the epsilon, it can only be, the left-hand side could only be S. Okay, so then of course, if you have these rules, then we have to remove them. But after we remove them, we have to look at the existing rules that contain A at the right-hand side, and then we have to replace that A with epsilon. If you have multiple A's, you're going to replace those A's with epsilon 1 at a time, and then 2 at a time, and then, of course, in all combinations, and then finally replace all A's with epsilon. So it's in combination. So let's look at this example here. So we have R, UA, VA, W. So A appears twice. So first we pick this A, and then we pick this A, and then we pick both. Okay, so there's all combinations. So we pick this A, we have this, right? Because we replace that A with epsilon. And then we pick the second one, replace it with epsilon, and we pick both, right? So that we generate this. So these are the new rules we need to add. Okay, and then if you have a singleton derivation, A arrow B, of course, obviously, we want to remove it. And after that, we are going to add, now if B actually can go to a terminal, then we are going to, after we remove this, we have to say that A can go to this terminal directly, okay? All right, so now continue. So now we have removed all these singleton. So this is the singleton rules. We have removed these rules. Now suppose you have rules at the right-hand side, you have 2 or more symbols, either variables or terminals. Okay, so now we are going to convert these rules into the rules in these forms. Okay, so what we're going to do here is this. If K is equal to 2, okay, so if K is equal to 2, then we can just So we can just use two new variables. Okay, so A, for instance, we get capital U1, right? If we only have two, and you just replace, well, actually, we can just say for k greater than or equal to 2. Okay. And this UI could be variable, could be epsilon. So what we're going to do here is we separate it into two parts. So if we only have two, so then so when this so what we are having is A go to U1, A1. Let's say just greater than 2. So A, we can replace U1, and then this whole thing, we add a new variable A1. A1 represents U2 up to UK, and then we recursively do A2 go into U2, A2. A2 then represents U3 up to UK, right? We keep doing it until the last one, which is A k minus 2 goes to UK minus 1 UK. And so finally, if UI is in sigma, okay, we replace that UI with a variable capital UI and add these rules to it. Oops. Similarly, if k is equal to 2, okay, okay, put a k equal to 2, then only these rules can apply. Okay, so because at the end it should be U1 first, so only these rules. Then of course I use the same way to handle it. So we can add a k is equal to 2 is the same thing. All right. So this is an algorithm, an efficient algorithm, because your given grammar only contains a finite number of rules. And each rule, of course, the length is a finite. So the algorithm is efficient. Now let's look at an example to use these. So use this algorithm to convert a context-free grammar to an equivalent context-free grammar in the Chomsky normal form. Okay, so here, okay, is a given grammar. So S goes to ASA, small ab. Okay, A goes to B or S, and B goes to small b or epsilon. So now our first step is to add a new star symbol S0. So that's the ones that's added. And everything else is the same. And then the next, we're going to remove the epsilon rules. So we have B epsilon, right? B epsilon. So then we are going to look at in the existing rules that contains B at the right-hand side. So we have this one and that one. So we have to, so we keep all the existing ones, but also add new ones. In this new ones, we will need to replace B with epsilon. So that means we have, this is existing, but then, oops, sorry, here. And then we gotta replace that B with epsilon. So we got A. So this is a new rule added. So anything in bold is a new rule. Okay, so likewise, B appears here. So that means that we need to replace a B with epsilon, but then you have this, right? So this rules is being removed. So you have this, but then A arrow epsilon is also needed to be removed. So in this case, we are going to see which rules contain A at the right hand side. So we have 1. So now, of course, we keep this, but we add a new rules by replacing this A with epsilon, replacing that A with epsilon, and replacing both A's with epsilon. So we got 3 new rules added. So one is SA. The first A is replaced with epsilon, by epsilon, and the second AS, that means the second A is replaced by epsilon. And then both A's are replaced by epsilon, and we get S. Okay, so these rules are removed. Okay, so then we are going to remove singletons rule. So we have A arrow B, so we need to remove it. So when we removed it, we look at this B. Now B can go to small b, so that means that after we remove this, we have to add A arrow B back. Okay, so that's okay, so remove unit rules. Okay, it's called unit rules now. Yes. So we get the A goes to B. So so this has to be removed. Okay, but we also have another S going to S, right? Yeah, this has to be removed. And for this S, you look to see whether this S can go to a terminal. There isn't any, so just simply remove it. So this just removed. And then we are going to look for other ones. And S0S, okay, so this is the same thing. We got to remove that. So that's removed. When this removed, you can see here that this S going to ASA, ABA, AS, right? So when this a unit rule or singleton rule is removed, we got to put this back to this S. So that's what we have. So these are the new rules added. This is gone. And then finally, we remove this. We add, because B goes to small b, so we add a small b in here. Okay, now do we have any more? Yeah, we still have one more here, AS, so we got to remove that. Since S doesn't go to any terminal, so just simply remove that S. Finally, we're going to look at all the things at the right-hand side that contains now 2 or more symbols, either variable or terminals. So, for instance, for this AS1, so you can have S0 going to A1, and then A1 going to SA, right? So you have this ASA here, ASA. You add a new rules. So this is you go S0 to A1, sorry, AA1. Remember, so we keep this in AA1. Oops. And A1 is SA. Okay, so that's that. And then look for another one. So we have this. So this is the same. So we already have that. We just added to it. ASA is the same. So that's it. So we get to replace all of these by these rules. So the first one, ASA, is replaced with AA1. And the second ASA also replaced by AA1. And then the third ASA also replaced by AA1, and A1 goes to SA. So that's it. So now here you see that it is in Chomsky normal form. Okay, so that is the end of this video. So in this video, we look at three things. One is the definition of context-free grammars, and then we look at the concept of generation or derivation by context-free grammar, and then we look at Chomsky normal form. So any context-free grammar can be converted to an equivalent context-free grammar in a simple form called the Chomsky normal form. And of course, these are three major things. And then we also explained why such rules are called context-free, because these rules at the left-hand side, you only have a single variable. So that means that it is context-free. Okay, that's it.